Welcome to Math 2318, Section 1.10. In this particular section, we look at two practical examples using the techniques that we've been looking at. In question 1 here, we have two cereals. These two cereals have a certain number of calories for each one, a certain amount of protein for each one, a certain amount of carbohydrates, and a certain amount of fat. What we'd like to find is an amount of cereal A and an amount of cereal B where the sum of the calories is 340. The sum of the amounts of the protein totals to 14. The sum of the carbohydrates totals to 58, and the sum of the fats totals to 14. So we'd like to figure out how much of cereal A and how much of cereal B. So we write down the equations that represent that situation. Put them in our matrix. And so I don't see any ones. So what I did is I saw row 4 here can be divisible by 2. And so that became my first row. Row 1, I'm going to divide that through by 10 to reduce the number size. Row 2, nothing to do with it. And row 3 here, I noticed that I could divide everything by 2. Doing that, I then use this 1 to make a 0 underneath it by multiplying by minus 12, minus 4, minus 9, and adding. Alright, at that point I saw I can take each of these rows and divide by minus 25, minus 7, and minus 17, and I get all the same rows. And so if I use row 2, I can make zeros. So I'm using this one to make a 0 above it and 2 zeros below it. And so what I see is that x1 is 1 and x2 is 2 for the amounts of cereal A and cereal B. Alright, and in question 2, we have a problem from physics, from electrical engineering, where we have a circuit, and in this circuit we have some resistances. No capacitors, no inductors, just pure resistances. We have voltage sources. And in electrical engineering, we have something called Kirchhoff's loop law, which says if I sum up all the voltages around the loop, the sum of the voltages must be 0. Now we have certain directions here for each of these currents. If our current goes through a voltage source in this direction, where I'm going from the small line to the big line, then in that case that's a negative voltage drop. And if I'm going this direction, that's a positive voltage drop. And the voltage going across a resistance, there's a relationship that says V equals IR. So let's just walk around loop 1. So if I walk around loop 1, let's see. I've got 2 times I1, 2 times I1, 2 times I2, and 5 times I1. So each of these are times I1, and if you total them, there is 14 of them. Now you notice I1 is coming this way, I2 is going the opposite way, which is minus, so I get a minus 5I2. 2. What about the voltages? Let's see, this is a minus coming this way, another minus. So a minus 48. And by doing that, I get this particular relationship where if I move the minus 48 to the right. Looking at loop 2, you do the exact same thing. What about the voltages? Let's see, I'm going from this side across. That's a plus 31, a plus 17. All right, got that. What about the going through the resistors? Let's see, I've got this direction, so 5I2, 2I2, 3I2, 2I2. And so if you sum together all the I's, 2's, I get a 12. What about I3? Well, let's see. I3 is going this way, negative to I2. So that's a minus 3 I3. That's there. And along the top here, I2 is going this way, I1 is going this way, so a minus 5 I1. And so if you put all of that together, we get this equation. And now do the same thing for each of the last loops, 3 and 4. Trace the voltage drops across each of the items, whether it's in the positive or negative direction. Once we do that, here are our equations. So I put them into Wolfram Alpha. So here's my equations. I used row reduction, which is what it looks like. And here's the result showing us what the current is for I1. In loop 1, the current I2. In loop 2, here is the current in I3. And finally, here is the current in I4.